Hey everyone, this is the second segment of the earthquake chapter. Um, Now we continue about the depth of the earthquake. The deepest ever measured earthquake was about 670 kilometers deep down in the earth. We do classify the earthquakes into three groups related to their depth, the depth of the focus. Remember, the focus is the point at which the energy starts to get released. Uh, Logically, remember we said that every single earthquake is a fault line. So to have a fault line, the temperature has to be relatively low, the earth has to be rigid. So logically, whether you have cold and rigid crust deep down. Yeah, the only place you could have it is when you have a rigid cold lithosphere plate going down under the other one, and that's the only place. So we must have very, very few deep focus earthquakes, and that's the case. So we divide them like shallow, intermediate, and deep focus earthquakes. But as you can see, most of the earthquakes are shallow focused, like 0 to 70 kilometer. More than 85% of the earthquakes belong to that group. Some intermediate, that's about 12%, that's 70 to 350 kilometer deep. So the very deep focus earthquakes is only 3%, and that is between 350 to 700 kilometer. The next topic is like, how do we measure the strength of the earthquake? We have two ways we still use. One is the Mercalli or intensity scale, and the other one is the Richter scale. The intensity scale was done by European earthquake measurers, people who actually measured the energy of the earthquakes, and the way they measured it was based on the damage it caused to the human society, like damage into buildings, how many people did it kill, and so on. So they named it Mercalli scale after the guy who worked on it, and the Mercalli scale numbered with Roman numbers from 1 to 12, and 1 is nothing and 12 is total destroy. Everything is totally destroyed. So this goes from 1 to 12, and at 1 everything is completely at 1 nothing happens, and 12 everything is completely destroyed. There is a problem with the Mercalli scale because what if there is no any kind of human building where the earthquake happens? Then you cannot measure it, am I right? So that's a problem. Now the other problem is that, like, because of the strong building code in San Francisco, if there is a 7.6 earthquake, I mean, I'm talking about Richter scale, which is coming up in a minute, but everybody understands that. That's a big earthquake, but people in San Francisco just look up and they say, oh, there was an earthquake, and work further. On the other hand, if the same earthquake happens in Haiti, then every building collapses and just about everybody dies. So you understand that the difference between the different building structures and building codes is going to be a very different looking damage, if you wish. So therefore, that is a very, very subjective scale, and lately most people uses the Richter scale. So here is the Richter scale. The Richter scale or magnitude scale were first proposed by Charles Richter and Gutenberg, and they wanted to make a quantitative measure which actually measures the amount of energy which gets released during an earthquake. Today, the modified version of this Richter scale has been used all around the world. You have to understand that the Richter magnitude is related to the maximum amplitude of the S waves measured on the seismogram, and it has to be taken into account how far the earthquake was measured from that seismogram. from that seismograph. So the other thing is that it's a logarithmic scale, which means it's not a linear scale, which means a magnitude 7 earthquake is 10 times larger than a magnitude 6 and release over 30 times more energy. So it makes a big difference between the numbers. So you have to understand that. This picture shows you next to each other the intensity scale or Mercalli scale, right here, the 12, from 1 to 12 Roman numbers, and this is the Richter scale. So you can read how they compare. On the intensity scale, like 5 is where the chimneys start to fall off, and 12 is total destroyment. And in the magnitude scale, it's about the same. Like if you have about 4.5, 5.3, that's when the chimneys start to come down and you start seeing structural damages in the buildings. And this here shows you that the amplitude of the S waves is the base of the calculation to the magnitude of the earthquake. And here is the equation for the calculation, actually. And I will not ask this, so you don't have to worry about memorizing it. Next thing is the location of the earthquakes. Where would you have earthquakes? And this shows you the map of the US. And so you can see that most of the earthquake in the US occurs in the West Coast. Right here. Now, and of course in Alaska. Why? Yeah, Alaska is an oceanic plate boundary, so they are being pushed together and one is going under. The West Coast, if you remember, up here, it's oceanic continental, it's transform and divergent down here. So there's a whole lot of reason that you have that many red symbols. And if you look at an app on your iPhone or iPad, you can find the earthquake application and it will show you that every single day there is at least 5, 6 red earthquakes somewhere in the world. And all those are relating to plate boundaries. So just about every earthquake can be explained. However, you must understand that not every single one of them can be explained. Like here is this one. This is in Charleston, South Carolina. And there was a 7.6 earthquake there about 120 years ago. And nobody really understands why. There is no plate tectonic boundary, nothing there. So nobody knows, but for sure there is a very strong building code in Charleston, South Carolina. So you cannot build bridges unless it was checked by a seismologist. So make sure that it's not going to collapse if you have another 7.6 earthquake in the area. There's another interesting location, and this here is New Madrid. It's in Missouri. It's 1 hour south of St. Louis. Now, this place, about 150 or so years ago, had an 8.6 or so earthquake. So it was really a huge earthquake. Actually, it was related to a normal fault. And you have to imagine that if this is north, and this is south, and the Mississippi River is going from north to south. So this earthquake happened at New Madrid, and that was like it was a normal fault, so the hanging wall went down. And what made really interesting is that the Mississippi River, because the rivers are flowing down, because the block went down, so the Mississippi River, instead of flowing north to south, it had to go toward the north for a little while in that area because of the block fell down toward the north. So I guess people got really scared when they saw that not only that they had this huge big earthquake, even the river is going the other way now. So it was pretty scary, I bet. And this is the map. It shows you that most of the earthquake are delineating the plate boundary. Basically, they define the location of the plate boundary. That's how we know exactly where the plate boundaries are. Even though there are a couple of exceptions, most of the earthquakes are related to plate boundaries. And now we are at the effect of earthquakes. So make sure that you know all of them because I will ask it, so you have to list them all. The first one is the ground motion. And the ground motion is the trembling and shaking of the land that cause the buildings to vibrate. if you have big earthquake, actually you can see the motion going through the earth, and also the buildings are swaying. Uh, because of proper building construction can reduce the damage a great deal, building codes have to be very strict in special areas. So if we know that our area is prone to earthquakes, then you have to have special building code. Now, what does it mean that there is a building code? It means that the code will tell you how much steel has to make your building more strong than other areas. When you have steel in it, it's becoming more flexible, so you can sway it. The building can sway better without being damaged. The location of the building codes has to be really strict. So understanding where the earthquake zones are, you kind of understand where the very strong building codes are. And one more important thing, that the harder, it's much more safe when you have solid rock underneath. If there is an earthquake, if there is solid rocks underneath, it's much less dangerous than if it's an unconsolidated sediment. And I'll show it to you. This picture just shows you the swaying of the buildings during an earthquake. And that's just a couple of pictures of collapsed buildings. And here you can see the earthquake in Charleston, South Carolina. It was 1876. It was a 7.6 earthquake. Every single building which had 10 stories collapsed. The reason is because the 10-story buildings had the natural sway in the same period as the earthquake, and actually the sway got enhanced, and that's why those buildings collapsed. The next thing which we have to mention is the fire. You understand, when there is an earthquake, the gas pipes are going to be broken, and also the water lines. When the gas pipe breaks, you're going to have a fire, but because the water pipe breaks too, you have absolutely nothing to put the fire out. And this is how San Francisco actually burned down in 1906. The next thing is the landslides. Obvious, if you have a big earthquake where the shake is going on for a minute, you can have big landslide. Like we had one in 1959 Madison Canyon, and another one in 1917 Peru, which produced huge mud flow in the Andes. And this one here is Tacoma after the 2001 earthquake. You can see that there was a big mudslide right there. So this is not a safe place to be, especially not during earthquakes. The next one is the aftershocks. And the aftershocks are small earthquakes which are following a big one. And although they are smaller, they still can cause a lot of damage, especially if the original big earthquake caused some structural damage in a building. The small aftershocks actually can collapse that building. So that's why if there is an earthquake and you actually happen to get out of the house, you can never go back, because it could be damaged, which you don't see. So the aftershock can easily collapse the building. So you can never go back, at least for 2 weeks, into a building which survived the earthquake. The next thing which happens after earthquake is the tsunami. If the initial earthquake happens underneath of the ocean, the earthquake will, like just imagine you have a normal fault or reverse fault, or mostly just normal or reverse. Underneath of the ocean, if that happens, one block moves, that initiates a huge wave. It's called seismic sea waves. And the hurricanes are really damaging. They can have a wavelength of 400 meters, which is about like almost half a mile. I mean, it's a little bit too much. 400 meters would be 1,200 feet. That's about it. So that's the wavelength here, like from crest to crest. So that's 400 meters in a hurricane. The tsunami might have 100 miles wavelength, and it might move 450 miles per hour. And the wave height at the shore, where it's always higher at the shore, could be as high as 45 to 90 feet. 45 to 90 feet. The problem with this very high wave height is that with this wavelength and wave speed, there will be rising water for at least 5 to 10 minutes. And if you think about 90 feet is really, really high. So this causes a lot of damage. Like lately we had one in Japan, a really big tsunami, and that's what caused the problem with that nuclear reactor. And then before that, in 2004, that Bak State tsunami, which killed close to 200,000 people, that was the problem there too. What was really also major problem with the Bak State tsunami, that it happened at Christmas. And in the Indian Ocean, there is no tsunami warning system. So therefore, nobody knew, no one knew. And it happened mostly in the tropics. So a lot of tourists was on those islands. A lot of people died for no reason. It was really, really horrible. There are movies out there so you can watch it. And this just shows you how the tsunami, here is the earthquake, the fault line, and that's what initiates the wave. The next one is the liquefaction. When you have an earthquake and it happens in a coastal area where you have water-filled, unconsolidated sediment, the earthquake starts shaking the whole area, and the shaking causes this water-filled sediment to behave as a liquid. So anything which is heavy gonna go down, and anything which is light is gonna come up. So the buildings will actually go down, and sewage tanks and other underground construction such as coffins, which is horrible, but coffins will actually float on top near to the surface. So this is a couple of pictures of showing liquefaction. Especially this one is really cool. You can see this building if you look closely that basically just went down by one floor. Now, this is a very important picture, and I want you to really remember this. If you ever go somewhere where there is an earthquake, the safest place to be is when you have a hard rock underneath, like granite, sandstone, basalt, whatever solid, dense rock. Then the earthquake is going to be much less dangerous. If you are on a coastal, unconsolidated sediment area, it's much worse, much more dangerous. And to prove this, I'm gonna show you this earthquake which happened in California. This is the original epicenter of the earthquake, and this shows you 3 seismic stations. One is on the bay mode A. The next one, B, is in a little bit more consolidated sediment. And the last one, which is the C, is actually on solid rock. And look at the difference in the amplitude of the seismic waves. So definitely, when you have a building on the solid rock, the earthquake is much less dangerous than on the unconsolidated sediment. So if you ever go to California and places like that to move, you do not want to move to the beach. You want to move a bit further inland, but the earthquake will not be as bad as it could be on the shore. And this just shows you a safe building. This pencil-shaped building in San Francisco swayed more than a foot, I think that's how you say it, in the 1989 earthquake, and it didn't get damaged at all. Now, the prediction of earthquake, there is no such a thing. We cannot predict earthquake. You can monitor slight changes along fault zone. Usually you see small cracks forming. You can see the properties of the rocks changing, or you can see water level rising in wells. You can see the surface of earth tilting a little bit, but it doesn't pinpoint down exactly when it's going to happen. There was one earthquake when Chinese scientists have predicted that it was going to happen 5 hours before, and the way they did it was animal behavior. You know how animals have the 7th sense, and they know when something bad happening that they go away. So this is what the Chinese scientists saw, that the snakes leave their holes, the horses become really skittish. Um, so, you know, you cannot always go away when your horses get skittish, so it's just not the way it goes. What we have today is the so-called probability maps. The probability maps are showing areas of high probability that a big earthquake would happen. And as you can see, the one in 2004 was a high probability area mapped by the seismologists. But as I said, you cannot pinpoint, you cannot tell when exactly it's going to happen. So that's just the way it goes. Now, Virginia. Virginia has had over 160 earthquakes since 1977. And you probably all remember the one 2 years ago, 2011. I think it was September the 2nd. And it was a 5.8 earthquake. And everyone felt it. And you have your stories. And it caused damage in Washington, D.C. and other places close to it. The epicenter was in Mineral, Virginia. And as you can see on this map, just about every earthquake happens in that area. The other ones are right around us, basically, but they are usually small. These earthquakes could be related to the fact that the Appalachian is uplifting, and not very long ago, about 18,000 years ago, sea level was much lower, and North America was covered with like 4 kilometer thick ice. And as the ice is melting, the continent is rebalancing. So that also causes uplift, and it also causes energy being collected. However, because we have all the old fault lines, it actually gets released relatively early. So this won't let big earthquakes happen around our area. And this shows you this last earthquake, 2011, September 2nd. This is the epicenter to it, and this is the area where people could actually feel it. And I hope you enjoyed the earthquake presentations, and I see you in the next one. Bye.